An electron in isotropy has magnetic number m equals 0 and is a stable particle with mass. The only other property is its chirality, which is locked into the massive helix with angular momentum of Planck's constant. When it encounters a polarizing field, these axes are forced apart as one aligns, and phi changes from 0 to 90 degrees. This means that m equals 0 changes to either +1 or -1, which is spin up or spin down. Each blade has an angular momentum of 1/2 Planck's constant. Transitioning from a spin 1 to a spin 1/2 is an example of an enneagon transition. Enneagon transitions require a system to be two-dimensional, and bivectors spin in a two-dimensional plane. In this case, left external precession means the leading blade is right, which lines up. It looks just like a fermion, but it is not. It is still a bivector, with one blade randomized. In the bivector standard model, what appears as a fermion is actually a polarized blade of a boson. Fermions are emergent, not fundamental. If the helicity is reversed to right, then the leading blade is left, giving this term. It is clear that the helicity determines the chirality of the leading blade. However, this is only true outside the interaction plane. In that case, depending on the helicity, a fermion blade can be chosen to have left or right chirality. Within the interaction plane, the two blades remained locked as a spin 1 m equals 0. In a field, the boson remains an arrow of mass, aligned as a spin 1. When that impinges on the surface, chirality plays no role, and it imparts a quantum of energy. Outside the 1-3 plane, we have seen two cases. These lead to spin having definite chirality. It interacts with a target surface, which we assume, let's say, is covered with left receptors. The receptors and the boson have the same frequency and properties, or the same gauge. This means a boson with right polarized blade impinges on the surface, and the left receptor and the boson will have opposite chirality. They form a double helix of mass. This asymmetrical process follows Fermi-Dirac statistics, not due to particles, but due to chirality that builds mass. In contrast, if the left blade of the boson is polarized, then it coherently joins with the left receptor to give a torque to the surface. This is a symmetrical building process. We have matter, wrenches, and hammers from the bivector boson. For a random arrival of bosons, 3/4 of the time matter is built and torqued outside the plane, and 1/4 of the time the surface is hammered with quanta from inside the plane. However, by controlling the initial phase of the boson at the source, it is possible to differentiate between landing in and out of the interaction plane. Finally, I stress that an isotropic boson becomes a polarized fermionic blade. In free flight, the boson has polarized mass only. There is no charge, no helicity, but it retains the spin 1 as energy locked as mass. When encountering the field, the blades are pulled apart. Rotational kinetic energy and helicity return. In this process of unfurling, a geometric phase shift occurs, giving an imaginary component to the magnetic moment. This is like the covariant derivative in quantum field theory, which is complex. Complex indicates charge. This is an example of Berry's geometric phase. Charge and kinetic energy emerge in a field, and the chirality of the leading blade is opposite to the helicity. The deeper I look at spin, the less quantum it becomes, and the more clearly it reveals its classical and geometric core. At its heart, spin is a classical bivector. It's a real rotating structure defined by two axes. There's nothing inherently quantum about it. The so-called quantization doesn't come from spin itself, but from the energy confined within that structure. When we linearize the Klein-Gordon equation, the Pauli matrices emerge, not as mystical quantum operators, but as the algebraic description of chirality. It's at this point, when space transitions from reflection to parity symmetry, that quantum behavior begins. The Pauli matrices simply encode which hand, left or right, the spin axis takes under parity. All I say here is backed up by geometric algebra, and the math is very easy to visualize, especially when compared to the standard model. So I will present next a brief treatment of the classical background and the full dynamics from the geometric algebra that justifies the discussion up to this point.